Hello, everyone. Today I'm going to introduce you our work on human and AI perceptual differences in image classification errors. Artificial intelligence has achieved remarkable success across diverse domains, from object detections and image generations in computer vision to sophisticated conversational-based large language models. Given these advances, a crucial question emerges as AI excel at many routine tasks. Should we still value human labor contributions, or we can simply delegate these simple tasks to AI? The human computation community offers an important perspective. Human and AI exhibit fundamentally different strengths. While AI excels at mathematical computations and pattern recognition, humans possesses unique capabilities in real-world reasoning and contextual understanding. In our work, we try to understand how humans and AI could see the world differently and find opportunities for human AI teaming from an AI researcher's perspective. We approach this problem by looking into a very basic computer vision task, image classification. This supervised learning methods relies on human annotations. However, label noise is inevitable. It could be caused by ambiguities in images, different understandings or ideas among various annotators, or simply errors from human labor. Since this talk involves a lot of comparisons in between humans and machines, I use these type of icons to represent human annotators and machine classifiers for the rest of this talk. We train the machine classifiers to recognize CFAR10 images. Instead of using clean labels provided by the original dataset, the CFAR-N provides a noisy human-labeled dataset for a better representation of the real world. We use labels provided by CFAR-N for training and evaluate the results in the original test set. The label noise community has provided robust algorithms for label noise learning. We tested a wide range of methods in our setup. Not surprisingly, all of the machine classifiers perform better than a single human annotator. The three human annotators scored at around 82 to 83% of accuracy, while machine classifiers are like 85 to 90% of accuracy. This leads to the question we would like to ask. Can we eliminate human workers in this simple image classification task? Our first goal is to understand if human capability is merely a subset of machine's capability. We know the overall score from human annotators are actually lower than the machine classifiers. If the corrected labels from the human annotators are merely a subset of the machine classifiers' corrected labels, introducing additional human labors to this task would bring us no additional benefits. However, if we can find some non-overlapping areas, meaning sometimes the machine get it right, sometimes the human get it right, there is hope for complementary teaming in between humans and machines. To answer this question, we first look into the confusion matrix for their mistakes. Here, we present the confusion matrix between humans and humans, machines and machines, and humans and machines. As you can see, machines and machines show a strong diagonal line in the confusion matrix, indicating machines tends to make similar mistakes. Humans to humans, on the other hand, have a slightly stronger disagreement in their mistakes. While we compare humans and machines, we find the results go all over the place, indicating humans and machines are making very different mistakes, which implies they might see the world differently. Given the fact that humans and machines have different distributions of predictions, we would like to understand their performance on different kinds of samples. We first partition the task difficulty from the machine's perspective. Machine confidence. In image classification, a machine predicts the probability of a sample belonging to each class given an image. The maximum score is the machine confidence. Here, we show the machine and human performance on sample with low to high machine confidence. Although the machine have overall better performance than human annotators alone, we find that human annotators do a better job when machines have low confidence. We use another metric from the machine's perspective, a machine agreement. This number represents the consensus rate among other machine classifiers on a sample. We find a similar effect to machine confidence. If a sample is very difficult for other machines, the machine we're observing right now is more likely to fail also. Human annotators, on the other hand, are less likely to be affected by this. We also look into the task difficulty from the human's perspective, annotation time, and human agreement rate. If the annotators spend a lot of time, or the human annotators have lots of disagreements among themselves, that could imply this task is quite hard for the human annotators. However, we find a strong correlation in between the performance and the task difficulty in both humans and machines. In this case, this could suggest that if a task is difficult for humans, machine will have a hard time classifying these samples also. At this point, we know that perceptual difference between humans and machine classifiers exist in image classification. Our analysis showed that while single human has lower overall accuracy than machine classifiers, their perception is not merely a subset of machine perception. So we cannot eliminate human labors just yet. Sensitivity of the results. To understand the sensitivity of our results, we train the machine classifiers with different sets of human annotations and vision backbones. To ensure the fairness in this task, we create a balanced set to reduce the bias potentially caused by the majority of correct cases. A balanced set is a subset randomly selected from a test set, which includes half correct and half incorrect answers. Our results shows that human annotators and machine classifiers has lower probability of agreeing, while machine classifiers have much higher probability of having the same prediction under both experiments. From here, we know all machine classifiers in our test were strongly correlated to each other, while human classifiers produce a different distribution of answers. Our understanding study find that although human annotators have lower overall performance than machine classifiers, complementary teaming is still possible due to different expertise in different samples. We would like to show the Oracle mode for the human AI teaming we're presenting. In this mode, both machine and human make predictions. And we pick the best predictions based on the ground truth answer. Our results shows that introducing annotators from a single person, introducing annotations from a single person can increase the machine performance by 7 to 11%. For example, the CE methods increase from 84.5 to 95.9 with a single human. Co-teaching increased from 89.95 to 97.3. By aggregating results from three human annotators, the performance can go even higher. On the other hand, adding an additional model gives us limited benefits. For the realistic mode, we introduce a simple post hoc teaming strategy. Essentially, we trust the human predictions when machine confidence is lower than a threshold. Our hypothesis test finds zero point 0.6 is an optimal value across methods. Practically speaking, about 20% of all the tasks needs human involvement, while others remain automatic. Here we demonstrate a specific example of teaming up one type of machine with either an additional human annotator or with a second machine. This chart shows the teaming performance between the two contributors. The values on the left-hand side indicate that we always trust the original machine, while the right-hand side indicates that we always trust the prediction from a teammate. We can see there is clearly a complementary teaming effect in between machine and human annotator, even when the annotator has a lower overall score. Machine-to-machine teaming, however, has very limited benefit from this. The performance gain is primarily caused by the dominant machine. Our results shows that human and AI teaming in the realistic mode significantly outperform machine-to-machine teaming. For machine-to-machine teaming, we observe only 1 to 2% of performance gain in the realistic mode, while adding one additional human gives us much more improvement. While with a higher human budget, say using 3 human annotators and aggregating their answers through majority voting, we're able to gain 4 to 8%. Notably, the highest human AI teaming performance has already achieved 95% of accuracy in the realistic mode. To summarize our work, we show that perceptual difference between human and machine classifiers exist in image classification. Our analysis showed that while a single human has lower overall accuracy than machine classifiers, their perception is not merely a subset of machine perception. So we cannot eliminate the human labors just yet. All machine classifiers in our test were strongly correlated to each other, while human classifiers produce a different distribution of answers. Given these differences in expertise, we demonstrate that human-machine teaming can lead to greater accuracy than machine-to-machine alone. Thank you for listening to my talk. Feel free to reach out for further discussions.